Hello, for today's video lecture we're going to talk about solving systems of equations with matrices. Systems of equations and matrix equations, we're going to talk about that first. So kind of any set of related equations, if we have a bunch of equations and they all kind of share some variables, that's going to be known as a system of equations. So an example of a system of equations is going to be usually the equilibrium equations that we get, particularly when we're working with structures when we've got lots and lots of equations and we're going to need to solve all those equations, when we're going to have lots of variables kind of shared between all those equations. So any system of equations that we have has the potential to be rewritten as a single matrix equation, and then we can solve the matrix equation rather than solving all of the equations kind of individually with algebra. So this provides an alternative approach to just kind of powering through with algebra. So to rearrange the equation so that all constants are on one side, to rewrite the system of equations, the matrix equation, we're going to first start by rearranging our equations so that all the constants are on one side and all the kind of variables with coefficients are on the other side. It's also useful to make sure those variables kind of show up in the same order consistently in each equation. So here we've got fax plus fbx equals 0. That one, if we kind of rearrange this, it's going to stay exactly the same. Fax plus fbx equals 0. For this second equation, I had fay minus 8 equals 0. The one thing I want to change here is I want to move this constant, this 8, over to the other side. So I'm left with fay equals 8. Third equation down here, I've got negative 16 plus 4 fay plus 8 fax equals 0. And I've done two things with this. First, I've moved this 16 over to the other side here, so the constant is on the right. And second, I've switched the order of the two variables. So here I had fax, so I'm going to put fax first and then fay. So once I have kind of them rewritten in this very specific kind of fashion, I can start rewriting this as a matrix equation. And we're going to put all of the coefficients, so over here on the kind of left side of our equations, we're going to have all the coefficients before our variables. And so this is going to go in, these coefficients are going to go in an n by n matrix, where n is the number of equations, and it should also be the same number as the number of unknowns that we are solving for. So each row represents a single equation, each column will represent a single variable. And we put zeros where the kind of variable does not exist in that equation. So here let's look at this first row. I have fax plus fbx equals 0. So I've got I've decided my first column is fax, second column is fay, third column is fbx. I've got 1 times fax. I don't have fay, so it's 0 times fay. And then 1 times fbx. So those are my coefficients for the first row. On the second row, I've only got fay, so it's 0 times fax, 1 times fay, and then 0 times fbx, so I don't have anything in there. Third one, I've got 8 times fax, 4 times fay, and I have 0 times fbx. Alright, so I've got my coefficient, or my A matrix, set up in this fashion. Next, I'm going to put all of the unknowns into a vertical, what I'm going to call the variable matrix. And so this is going to be the same order that I used in my columns. So this is what I'm solving for. I'm solving for fax, fay, and fbx. So I just list those in the same order that I had them up here. And finally, I'm going to put all the constants on the right side of the equation into an n by 1 matrix. So I'm just going to list those in order. It's going to be 0, 8, 16. So 0, 8, 16. And so now I've taken this equation, or sorry, I guess these equations originally, kind of rearranged it a little bit to get it into kind of an easy to read fashion. And then I've rewritten these equations as a single matrix equation. There's only one equal sign in this matrix equation over here. Alright, so now that I have my A matrix, my X matrix, and my B matrix, I'm going to go ahead and try to solve for x, because x has all the variables that I'm looking for, and I'm looking to solve for. Alright, so I got the general form, a times x equals b. And to solve this, if it were just scalar values, I'd simply divide both sides by a, and that would give me x equals b over a. To do this with a kind of matrix equation, I need to take the inverse of matrix A. And so if I take the inverse of matrix A and I multiply that by both sides, so inverse of A times A gives us what's called the identity matrix. It's kind of like the matrix version of 1. And that kind of cancels out. I can get rid of that. And then on the other side I have A inverse times B. And so since these cancel each other out, I'm left with x, which is what I'm looking for, is equal to A inverse times B over here. Alright, so I'll need to find this A matrix, which I did before, take the inverse of that. And taking the inverse of a matrix can be done by hand, but usually if we have a very large matrix, like I've got 10 equations with 10 unknowns, I'm not going to want to do that by hand. But computers are very good at doing the inverse matrices. So if I can do something like MATLAB, do A inverse times B, as long as I have those set into the computer, it can do it very, very quickly. And it can solve for x, and x is going to be, again, the matrix consisting of all the results. So it's going to have f(x), f(ay), and f(bx). It solves for all the variables I'm looking for at once. Alright, so why would I use matrix equations, particularly with computers? There's two main reasons we'd want to do this. Number one is simply if I have something like 13 equations, 10 equations, if I have a lot of equations, and I try to power through with algebra, generally setting it up as a matrix equation is going to be a little bit faster than solving it all by hand. So it takes more time to set up, but when you solve it, particularly with a computer, it goes very quickly. Second, and probably more importantly, if we make a small mistake, so if I kind of miss a minus sign, it should have been negative, and instead I wrote it as positive, and I'm powering through with algebra, if I make a mistake early on, it might impact later equations, and I'd have to kind of redo all of that algebra for that one little mistake. If I've set this up in something like MATLAB, where I can save my results, I can go back, I can change that minus sign when I realize I made the mistake, and then kind of hit the run button again, and it solves it all over again. So I've fixed my mistake in a matter of seconds, rather than taking another like 20 minutes to redo all of your algebra. So that would be the two main reasons you use matrix equations, particularly when we're working with very large systems of equations where we've got lots of equations, lots of unknowns. So with that, that's all I have for this video lecture. Thank you for watching, and I hope to see you again.